Hello everyone. In this video we will be doing one half of an equivalence proof. I'll do the second half in a separate video. So the two statements displayed are quantificationally equivalent, and we can prove that they're equivalent, but it takes two derivations. In the first derivation, we'll prove the second sentence follows from the first. That means we'll derive the second as a target, and the first is its primary assumption. The second video will run the derivation, and it'll be a very different derivation in the opposite direction. So let's go ahead and get started. So in this first proof, we're going to derive the conditional for all x. If for all x px, then there's a y qy. We're going to derive that from the existential generalization. There's an x, there's a y. If px, then qy. That'll be our assumption. So at the bottom, we're going to need this conditional. If for all x px, then there's a y qy. Go ahead and hit pause on this video and copy down the problem on your own paper and come up with an idea for how to structure this derivation. And when you're ready, resume the video. Since our target sentence is a conditional, a good way to prove it is with conditional introduction. And that requires a subderivation. Our subderivation will start on line 2. So line 2, we'll assume the antecedent of the conditional that we want for all x px. Assume for conditional introduction. At the bottom of that subderivation will be the consequent of the conditional that we're after. There's a y qy. Go ahead and hit pause and see what you think the next few moves might be. And when you're ready, resume. Since we have only the existential generalization on line 1 and the universal to work with, there's no avoiding this existential. It's our primary assumption. So what we have to do is start working with it. And the way that we start working with existentials is by using existential elimination. That means we're going to start another subderivation. This will be an instance of the generalization on line 1. We'll drop the x quantifier, replace the x with a name a. It has to be a name that we're going to have isolated to the subderivation. That means it's a name that doesn't appear anywhere else in the proof. Of course, there are no other names in the proof, so we get to choose whatever name we want. So let's go to about there. On line 4, we're going to start another subderivation because on line 3, we just have an existential generalization to work with. And that's the rule for working with that generalization is the same rule we're just now applying. In other words, existential elimination. So we have to start another subderivation. Let's carry this to about here. Okay, that's another assumption for existential elimination. So I haven't filled in the target sentences here, but very, very often when you're using existential elimination, the target sentence for your derivation is just going to be whatever it is you happen to be after. And we happen to be after this existential. There is a y, q, y. Okay? So this is going to come from existential elimination, and this is going to come from existential elimination. Okay, and we'll fill out the annotation later. The puzzle now for us is going to get from this conditional to this existential. So why don't you hit pause on the video and see if you can work that out. It'll just take maybe 4 or so steps. Okay, so here are some of the steps that are going to help us along. You know, we have this conditional if PA then QB to work with. We also have this universal generalization for all x px. If we instantiate that universal to the name A by universal elimination, things really start moving. Gives us PA, which is the antecedent of the conditional in line 4. And that gives up QB, the consequent, from lines 4 and 5, conditional elimination. That gives us our existential generalization. So this is comes directly from line 6 by existential introduction. The rest of the proof, we're home free. We just have to be careful with these annotations. Line 8, where we copied the last line of the subderivation down along the next outer scope line, comes from the existential generalization on line 3 and the subderivation running from 4 to 7. So 3 and 4 through 7, existential elimination. When we do the same thing again, take there as a yqy from this subderivation and write it down along the next outer scope line, we're appealing to the existential generalization on line 1 and then the subderivation running from 3 through 8. So 1 and 3 through 8, existential elimination. Again, to make sense of these annotations, the existential on line 3 together with the subderivation that begins with an instance of the generalization on line 3, so 4 through 7. And then for the second application of existential elimination, we're looking at line 1, which is the existential generalization, and then the subderivation that starts on line 3 with an instance of that generalization, and it runs from 3 through 8. And then lastly, our conditional proof started on line 2 and ran to line 9. So that completes the annotation for this first derivation, proving equivalence. The next derivation will be in the next video.